So we were looking at this decision tree. What is decision tree? So we know that it consists of some root node, then there are some children nodes, and finally the leaf node where classification is available. So in last class we have seen up to, I think, selection of. Okay, so this was the point that we left with, how to construct a decision tree. So there are several algorithms that have been proposed for the above task. That is, we shall limit our discussion, but in this case we will limit our discussion to around these algorithms: ID3, say 4.5 card, and in general following questions arise to construct a tree. Now, should the feature be restricted to binary or multi-valued? Okay, so that is a question. Which feature should be tested at a node first? Okay, so that means when I start with whole set and then I need to pose a question, and suppose it is of type yes or no on a binary feature, suppose, then say I have a list of features like A1, A2, and so on. Say this is some feature A1, this is some feature A2 and A3. Out of this, I will ask one question on one feature here. So which one I should choose, A1, A2 or A3? So that is the main problem. Then I can divide the thing into two branches and then further question I can ask. So here, suppose I'm asking question on A2, then I can ask question here on A1, and then I can split. Maybe I am asking question on here A3, then I can split. Okay, so like that, when I reach suitably to the cleaner or pure nodes, that means here all samples belong to only one class, say omega 1, then I will declare this as omega 1, this may be omega 2, this may be omega 3, omega 4, and so on. So what is basically done at the beginning is we ask a question based on one of the features and try to segregate the original data set, say D, into two subsets. So this is D here, and this will be subset D1, this will be D2. Okay, so once I do this, then I further ask the question to make further divisions, say D11, and this may be D12, this may be D21 and D22. So we keep on dividing the set. So this was my big set. I divided into D1, D2, and this was further divided into few more sections like D11, D12, D21, D22. So we keep on dividing these sets till we reach a pure node. That means there is no impurity from other class. So when I divide, suppose with some feature, say A1, I divide this into two halves. Say there are some omega 1 samples, there are some omega 2 samples here in majority, but there are few samples of omega 2 here, maybe few samples of omega 1 here. So this division is not pure. Okay, so we further use some other feature to make the division pure and pure. So doing so, suppose I get everybody here as omega 1, everybody here as omega 2, maybe here again omega 1 or omega 2, then there is no further division required because everybody here is omega 2, everybody here is omega 1. Okay, so we try to divide sets or keep on dividing the sets or keep on creating branches in tree till we get a pure node. Okay, so which feature is selected first? That is a question, and we should choose we should select a feature such that this tree is as small as possible. So asking some question on A2 may be giving you a depth of suppose 3, that is 3 nodes are created from root. Asking question on suppose A2 may give you depth of 5, that is 5 nodes are required or 5 levels of nodes required to get pure nodes. Then first feature is better than the second one. So which is to be tested first? That we will see how to do it. Now when node is to be declared as leaf node, so that is the question. As I said, when you get a pure data subset, then you can stop. Now many times it is not possible that you will get a pure data subset at the last node. You have to have some kind of you have to have some impurity, and then you have to deal with it. So in that case, we decide the class of that leaf node based on majority. Okay, suppose there are 10 samples of omega 1 and maybe 2 samples of omega 2 in a last node or in a node where we are standing right now. Then I say, okay, let us stop or terminate the process of creating branches and let us declare this as a leaf node omega 1. So this is possible. And so that is the fifth question. If leaf node is impure, how to decide? So we decide with majority. Now how to handle missing data? That is also a problem. Now how to simplify tree if it gets complicated? So it is called as pruning method. So when your tree is very complicated, then how do you curtail the branches of this tree so that you make it very simple? So simple is better. It actually, when you have more complicated tree, it indicates that you are overfitting your uh, on the your training data set. That is, your training error is less, but test error is more. Then that is not useful. So a better system or a generalized system is that system where training error and test error are comparable. Okay, so if you have more training error, more training accuracy and less training test accuracy, then that is not desirable result. The most important feature is used at the earliest level of splitting. So this feature is such that it makes the most difference to the classification being the most discriminative. Okay, we will see with example how this is how this is important. That feature selection is basically done with the help of terms called like entropy or Gini. So we will see in few slides later on. At each node, data is split up and result into a new decision tree problem by itself. So as I said, you start with suppose data set D. This is a complete set suppose with 100 samples, and then you take some feature, ask a question, and you get some answer, and you split your data set into D1 and D2. Say some 60 features, 60 samples are here, and 40 samples are here. So this is now a new data set for you. This is a recursive problem, so you can solve this now D1 data set problem, and you can take some feature and divide it into some further subsets. So you can take this D2 and divide it. Now, once you divide it, say this is your D11 child of D1 and this is D12 child. So D11 child itself become a new decision tree problem. Then you can split it with the help of some new feature. Okay, so like that this will grow. So at each node, the data is split up and result into a new decision tree. Okay, so same algorithm will keep on executing in recursive way to create new branch. A really good feature divides the data into groups that are all positives or all negatives. So if you divide nicely, then you collect samples, say for example, omega 1 in one side. Say this is my complete D and I divide this D such that all omega 1 samples are in D1 and all omega 2 samples are in D2, then this is the best one. So that means within one step my job is done. So since I am getting pure nodes, I will stop here. So that is how we try to do. A feature that leaves the data with approximately same positive, negative examples as of the original. So it's not a good feature. Okay. So we start with suppose a ratio 50 or 50, say 50 omega 1 and 50 omega 2. This is my uh, structure of D, that is complete set, and then I make child say D1 with again same 50 50 and maybe D2 with approximately 55 45. So this is a ratio which is comparable to the parent proportion. So in parent node, the proportion of omega 1 and omega 2 is approximately same, that is 50%. And in children nodes, it is also the same. Then such kind of division based on some feature which is giving you this division is not useful. So we want a feature which when used divides the data such that your data is divided into groups where all the samples are either belonging to omega 1 or they belong to omega 2. So that is our target. But that will not happen in one step in normal cases or in uh, general. So we have to then further divide. It may of the now let us see this example. Uh, Now if I divide this sample space, so this is my complete data set D, and then I use feature X. So there are two features in this problem, and this say triangle is a symbol for say class 2 and maybe this is for class 1. Circle is class 1. Then if I decide that I will use feature X, and if I take this threshold that if something is greater than this theta, X greater than theta, then it belongs to one class, and then this belongs to one data set subset and this belongs to another data subset. Then you will see that this data set, which is a D1, and let us say this as D2. So D1 now consists of samples belonging to class 1 and class 2. D2 also have samples belonging to class 1 and class 2. So the division based on X feature for dataset D shown in the figure is not a good one. Now instead of that, suppose you take this feature Y and you divide your data into two groups using Y, then you see that this is a pure box where all the samples belonging to omega 2 are there, and on the upper side you have a pure box of D of samples belonging to omega 1. So this is a good feature for me, which is producing pure and pure samples in separated subsets. So this is how we need to select the feature. So instead of X, we should prefer Y as the first step so that you get subsets which are pure one. Now, if you do use by chance X itself, what you have to do is, so this is my starting node with D, then you have ask a question. If X is greater than some theta, then you have split of data for yes and no. Then you have one more node here. So this is done. This line is implemented here at that level, and now you get, say, this as D1 and suppose this as D2. So this is yes means is it is D2 and no means D1. Then you have to ask again question on based on Y whether you are greater than this Y. Okay, so whether you are greater than this Y, that we will ask here, and you will set a threshold, say let us say theta 1 here. Then you get two groups, say this one and this one. So these two sets are now pure, then you can declare them as omega 1 omega 2. Then you have some other threshold here which makes this D1 into two subsets, and you get omega 2 omega 1 here. Those are pure. So you need this much tree if you use first feature as X. Now if you use first feature as Y, then within one step only, because here you are drawing this line, this horizontal line at the first step. So Y is greater than theta, then immediately you get omega 1 and omega 2. So same problem is solved with only one question. That is, only one node is required, and these leaf nodes are for classes. Here you will see that you require 3 nodes in the tree and 4 leaf nodes. So this is more complicated structure than this one. So just selecting a proper feature can reduce your tree. Now if I want to suppose divide or create a tree for this kind of data, then what I do, I suppose start with X, because this is data which you cannot solve directly by like the earlier one. Here the data was good that you can draw one line to partition it into two groups. So this was separable with a line which is parallel to x-axis. Now since here it is not possible to draw a line which is parallel to x-axis or y-axis and then divide the data into two halves, because my problem is different. So here, since we are using tree structure with one variable at a time, so we have to deal with this using the same technique. So here what I do, suppose I ask a question, if x is greater than some theta, then this line is implemented. Then I get, say, two sets d1 and d2. So I created a node, and then I say, okay, this is some y and this is no, and two data sets d1 and, say, here I should say d2 and d1. So now we have two separate problems with two data sets, subsets d1 and d2. Then I take d2 set and then I use feature y. So I ask the question, if y is greater than some theta, then based on this I get this data set, say d21, and this data sets d22. So this is one group and this is another group. Now the upper one is pure one, so we can declare it as a leaf. And then I decided that, okay, out of three, two belongs to one class and one belong to the other class. So I will stop here and then I will declare this as, say, class, say blue class. So this is orange class and this is blue class, since majority here is blue. So like that, I created two nodes here, omega 2 and omega 1. So this branch is now over and there is no further split. But this d1 is left. So I take the feature y, which is left. X is already used. So I take the feature y and set a threshold, some theta, 2, and then I divide it uh, into two groups. Then I find that, okay, with if I put line here, then this is pure blue group and this is pure orange group. So I created two subnodes. So these are leaf nodes for this section. Okay, so this is my complete tree for the given problem. I hope you got the basic idea how to divide data. At each node, the query which makes the data to subsequent node as pure as possible. So that we take into account. Now, how pure is your data, say before division and after division? How to measure it? So we have different measures to do this. So first of that is entropy. So basically ID3 algorithm is using this entropy as a measure of impurity of data. So this is given here is minus summation of j, where j is categories from 1 to, say, capital K. Suppose there are 3 classes, 2 classes, or 5 classes. So accordingly K will be set. So K is 2 means you are dealing with 2 classes. If K is 4, then you are dealing with 4 classes. So this entropy will be running from 1 to K, j equal to 1 to K, say probability omega j into log to the base 2 probability omega j. So that will give you the entropy. Now second, we will see this detail again. The second measure is called as variance or Gini impurity for multi-category in this is basically used in CART algorithm. So it is nothing but the variance or covariance between two groups. So here there are two probabilities, probability of omega I into probability of omega j, where I is not equal to j. So this product is actually variance or covariance. Now this is equal to 1 over half 1 minus summation j equal to 1 to capital K p square, that is probability of omega j square. So if these two things are equal, so if you have many classes, then you will use this second one. This is called as Gini impurity for multi-category. So we are going to use this in CART algorithm. And this first one is used in ID3 algorithm. And the usual misclassification impurity is 1 minus max of j probability omega j. So this is used in normal way. So but the measures 1 and 2 are basically used in decision tree. Now you may be knowing this concept of entropy. So whenever you have more ordered set or more ordered kind of thing, then you have less entropy. So when you have more random things, then you have more entropy. So less uncertainty, more entropy. Okay, high uncertainty, that is less ordered things, then high is entropy. Okay, so here you have organized kind of arrows, then you have less uh, uncertainty, so less entropy. But here you will see that there is highly uncertain thing, so you have a high entropy. So entropy is an important concept used in physics in the context of heat and thereby uncertainty of the states of matter. But later, with the growth of information technology, entropy became an important concept in information theory. The entropy concept in information theory was firstly coined by Shannon in 1850. The first time it was used to measure the information content in the message. To deal with classification job, entropy is an important concept which is considered as an information theoretic measure of uncertainty contained in training data. So with those 3 or 4 equations that we have seen for entropy, then Gini or variance and misclassification. So what this plot has done, this is a plot for 2 category problem. So there are only 2 classes, omega 1 and omega 2. So what is done on x-axis, the probability for say omega 1 is varied from 0 to 1, and on y-axis this entropy, Gini and misclassification index, they are plotted. So when you have say omega, probability of omega 1 suppose equal to 0, that means there is no chance that you get omega 1. So that time you will get 0 entropy. Okay, so there is no information in this when there is certainty that you don't get omega 1. Similarly, when you have omega 1, probability of omega 1 equal to 1. That means every sample with you is of omega 1. So probability of omega 1 is 1. So at this position. So again, there is no information in this. So the entropy here is again 0. So for the two extreme things, you have 0 entropy. But when you have 50-50 chance, that is probability of omega 1 is equal to probability of omega 2 equal to 0.5. So at this position, you will see that there is highest entropy or highest uncertainty. So this first graph is the upper one is of entropy, which is used by IDE3 algorithm, and the second one, which uses the covariance, is slightly computationally easy. It don't require this log calculation. So basically that is popular because of that is used in CART. Okay. And this last one is the normal misclassification. Okay, so we will take a small example when patterns are equally split into two subsets, that is omega 1 and omega 2. So the entropy here is, if I use this formula, is maximum, that is 1. When all patterns belong to one branch, that is either omega 1 or omega 2, then entropy is 0. When 10 patterns are split into three classes, suppose there are 10 patterns which are split into omega 1, omega 2, and omega 3 as 4, 5, 1, then the entropy using this formula, so 1 for k equal to here 1, 2, 3. Okay, so this or j equal to 1 to 3, you will get entropy as 1.36. Now, if we have a training data set which is divided into k groups, then the entropy calculation is like this. The above formula should be summed over non-empty classes, that is, classes for which probability is not equal to 0. So the entropy is always a positive quantity. It takes its minimum value 0 if and only if all the instances have the same class. That is the training set with only one non-empty class, for which the probability is 1. The entropy takes its maximum value when the instances are equally distributed among k possible classes. So if there are two classes, then k is 2. So we have zero point 0.5 and zero point 0.5 probability. If there are three classes, then it will be 0.33, 0.33, 0.33, and 0.33. So that it will be maximum. Now, as an example of entropy of a training data set, and this example we are going to use for further study. So give some attention here. OPTH dataset, ophthalmic dataset. Consider this dataset which has 24 instances, and this dataset is encoded actually for age, young, middle age, and old. We have three values, and they are coded as 1, 2, 3. Okay, so this 1, 1, 1 here indicates young actually in the table. The second one is middle aged. So this one is middle aged. So like that, we have another level as 3, which is old. Then there is feature number 2, which is eyesight, and then it has two values, so they are coded here. Then this feature, and then use type. So we have in total three features. All of them are coded in numbers for simplicity. Then actually we have the last column here as the class omega I, which has three values: contact lens, normal, glass, and nothing. So 3 indicates here it's nothing. So the data here is arranged like this. This is sample for some particular person number 1, and this is sample for person number 2, and there are features, 4 features here, and the last one is the outcome. So a coded form for all values of attributes are used to avoid the cluttering in the table. So if I write, say, all the values here, it will be very difficult to understand. So I just code it accordingly. So there are 3 classes and 4 instances with class 1, 5 instances with class 2, and 15 instances with class 3. So out of 24, 4 with class 1, 5 with class 2, and 15 with class 3. So if I use the entropy formula and write for j equal to 1, 2, 3, then you will get this expansion of that formula. And if you substitute proper values, so you will get entropy as 1.3261. Now see how it is done. Since it is 4 out of 24, so the probability for omega 1 is 4 by 20, and log the base 2 into probability minus 524, since 5 instances out of 24, so 5 by 20 into log to the base 2 into 5 by 24, log base 2 of 5 by 24 minus 15 samples of omega 3 out of 24 into log to the base 2 of 15 by 24. So if you calculate this, it will be 1.3261. So this is the entropy in the table itself. Okay, so in this table we have this much entropy. So entropy of this table is 3.621. Now in tomorrow's class, we will split this data using some feature such that this entropy after splitting gets reduced. Okay, so we will keep on splitting this data into smaller sets such that overall entropy after splitting gets reduced, or it will be less than this 1.3. Now how to do that, we will see it tomorrow. So let us start here.